All right, here we go. Counting permutations and combinations. First, we'll start off with counting and the idea that Mary has the following clothes in her closet. For shirts, she has a red and an orange. For pants, she has white, black, and gray. And the question here is, how many different outfits could she make? Well, we could just start listing these out then, right? Assuming every shirt goes with every pair of pants, her red shirt could go with the white pants, her red shirt could go with the black pants, and her red shirt could go with the gray pants. Okay, that's everything with the red shirt. Now we'll do the orange shirt. The orange shirt with the white pants, the orange shirt with the black pants, and the orange shirt with the gray pants. And that's it. I've extended all the possibilities. That's it. We wind up with 6 different possible outfits. And we just listed them out. We counted them. And this is counting after all. Probably pretty comfortable there. You can let me know if you have any questions. My next question for you, though, is, okay, well, what if she had 7 different color shirts and 5 different pairs of 5 different colored pants? Well, I don't want to start listing those out. I mean, just the shirt colors, red, orange, let's see, Roy, yellow, green, blue, indigo, violet. And now I want to pair those up with all the pant colors. No, I don't want to list these out. This is too much trouble. There's got to be a better way. Let's think about that better way. In the last problem, she had 2 choices for shirts and 3 choices for pants, and we came up with 6 total outfits. Your instinct is correct here. What's the shortcut? Instead of listing them out, what could we do? Excellent. Zara, Riley, Caroline, you're all right. We are going to multiply. Our shortcut is multiply. And Riley is exactly right. If she would have had 7 different shirt colors and 5 different pant colors, then we would just multiply those and see that she would have 35 different outfits that she could make with those. So our shortcut here is to multiply. This brings us to a really important mathematical idea called the fundamental principle of counting. What the fundamental principle of counting is if we want to know the total number of outcomes, we find the number of choices for each stage in the problem. For Mary, that was shirts and pants. Those were the different stages in the problem, the different things that she could pick from. Find the number of choices for each stage and then multiply the number of choices together. So that's our fundamental principle of counting, and we're definitely going to encounter problems where the fundamental principle of counting is going to come in handy and be valuable. For example, a code for a garage door consists of 4 digits. How many of these codes are possible? You don't necessarily have to do this, but it's something that I kind of like to do for these is, okay, I can see it's a 4-digit problem, so I'm going to go ahead and set up my 4 places. These are the 4 different places that are involved in my code. I'm going to enter a digit here, a digit here, a digit here, and a digit here. Those are the 4 digits that I'm going to enter. My first question to you is this. How many different possibilities are there for that first number? How many different things could I enter as the first one? And this could be an ATM pin or, anything along those lines. Very good, 10. A lot of times students will say 9 here because you forget about the 0. Excellent work. Don't forget about the 0. We have 10 different possibilities for that first digit. How about this next digit right here? How many numbers are possible? Very good. Excellent. There are 10 here. And then, as y'all have probably figured out, there are 10 here and there are 10 here. When we want to know how many different garage codes are possible, we're using the fundamental principle of counting, and we're going to find a number of choices for each stage and then multiply those together. And we'll have 10 times 10 times 10 times 10, which is 10,000. If you're thinking 10,000 different possible garage codes, seriously? That's reasonable. A lot of the answers you'll see today will feel like there can't be that many. That's such a big number. Well, let's look at them. Let's say we start with 0, 0, 0, 1, 0, 0, 0, 2, and we just keep on going until we get to 9, 9, 9, 9. Well, that's 9,999. This says there's 10,000. Oh, right. We could have all 4 zeros. And so there's our 10,000 different possible garage codes. You're not going to necessarily be asked to list them out, but sometimes listing them out like that can give us a little bit of comfort with, boy, that's a really big number, 10,000 different garage codes. You mean if I forget mine and I'm just trying at random, I've got to try 10,000 different codes? Yep, because there's 10,000 possible. When you see answers that are maybe a little bit bigger than your gut would tell you, that's okay. Chances are there's just that many. So what we've looked at here is the concept of the fundamental principle of counting, which is how many choices are there for each space, and then multiply those together. Do you have questions before I have you try one kind of like this one? All right. A license plate contains a number, 2 letters, and a number. So it's a pretty small license plate, probably not a huge population wherever this is. But this license plate is 1 number, followed by 2 letters, followed by a number. And my question to you is, how many license plates are possible? Just as a little reminder, there are 26 letters in the alphabet. I'm going to go ahead and make a poll for this and give you a chance to try it. This is definitely the type of question you could expect to see on a homework, a quiz, or an exam. So really good practice to work on it. If you get an answer that's not one of the choices, pick the one that's closest to yours. That way I'll know you've had enough time. We'll go another 30 seconds on this and then talk about it. All right, let's see how we're doing here. All right, not unanimous, but really strong agreement. That's terrific. Very good. All right, let's talk through it. Let me know if you have any questions. So we start out with the idea that, all right, I've got a number in this spot right here, and I could use 1 through 9. Don't forget about 0. So there's 10 possibilities for that one. And then letters, there are 26 letters in the alphabet. There are 26 letters, so there's 26 possibilities here, and then there are 10 possibilities here. Find the number of choices for each stage, and then multiply those together. And let's see here. We have 10 times 26 times 26 times 10, 67,600. So if there were a state or a location that figured they only need 67,600 total license plates, they could use this structure. Let me know if you have any questions on how we arrived at that number. All went great, so I feel like you're in a pretty good place with that one. I'm going to modify this problem just a tiny bit. A license plate contains a number, 2 letters, and a number. And for me, it just kind of helps me stay organized if I do this. It's not something that you necessarily have to do, but it helps me stay organized with what it is that I'm looking for. How many of these license plates are possible? And here's the new part: if repetition is not allowed. What that means is, once I've used a number, I can't use it again. Once I've used a letter, I can't use it again. On the surface, that might feel kind of overwhelming and like, wow, I have no idea how I'm going to do that then. So I'm going to ask you some questions as we walk through this. For this first number here, I haven't used anything yet. How many possibilities do I have for that first number? Repetition doesn't really come into play at this point. We're just looking at the first number on the license plate. Lorraine's one step ahead of me. Genesis, Emily, you're right. Yes, I have 10 possibilities for that number. And now when we get to this first letter, again, repetition hasn't come up yet. This is the first letter I've used. How many letters are available for me to pick from for that spot? Great, Natalie, Renee, Genesis, awesome. Thank you, Lorraine, very good. 26. I appreciate the interaction that y'all are giving me. That's helpful for me and great for you and helps keep you engaged and all that stuff. All right, here's where this repetition part comes into play. Now I'm doing another letter. Here's the key to thinking about this next letter we're going to use. I don't know what letter has been used in this spot. I just know I've used one. I don't know what it was, but I know I've used one of them. And so whatever letter got used here cannot be used again. With that in mind, how many letters do I have to pick from for this space? Excellent, Lorraine, Stephanie, Natalie, Nicole, great, very good. 25. That's the kicker with repetitions not allowed. I don't have to list out all the possibilities and figure out what's going on. The key is I had 26 to pick from for here. I used one, which means now I have 25 to pick from here. All right, Jason, I like it. Jason's one step ahead. When we look over here to this last number, how many numbers do I have to pick from for that spot? Very good. Carolina, Emily, Stephanie, that's exactly right. Using the same idea. I don't know what number got used over here, but I know I used one. Whatever it is, it's off the board. I can't use it now, which leaves me 9 to pick from for that space. And now I've found the number of choices for each stage in the problem. I'll multiply those together and figure out that there are 10 times 26 times 25 times 9. There are 58,500 license plates of this type if repetition is not allowed. It makes sense that it would be a smaller number. When repetition was allowed in the last problem, I would have had A00A and then A00B, and I could keep listing them out. Oh, wait, I did it backwards, didn't I? When repetition was allowed, I could have 0AA0 and then 0AA1, and I could keep going. Now that repetition's not allowed here on this license plate, I would have to say, well, my first one then is going to be, instead of 0AA0, it's going to be 0AB1 because repetition's not allowed. So I've eliminated some of the things that used to be possible. So it makes sense that we'd have a smaller number than we did in the last one. Sometimes with license plates, I like to use things like, the letter O can't be used because it could be confused for a zero. And so that just takes the letter O out of consideration right at the beginning. So be aware that those kind of things might happen with the conditions. But the main idea that we're talking about here is the fundamental principle of counting. Find a number of choices for each stage and then multiply those together. Any questions on what we've talked about so far and the fundamental principle of counting? Fantastic. All right, the concept of factorials might be new for you, might not, but 5 horses are in a race. In how many different ways can they finish? And we're going to talk through this one together. I'm going to ask you to help me out as I fill this in. So, I'm going to have first place, second place, third place, fourth place, and fifth place. And the horses are running around the track and they're all coming around the end. And how many of them are out there that could possibly finish here in first place? How many horses are possible to finish in first place? Excellent, Zara. And I understand what you mean, Escadar. There's only going to be one that does finish in first place. But right now, it could be any of the 5 of them. And so what we're doing here is we're looking at the fundamental principle of counting. How many different ways could this possibly happen? And so there are 5 horses that could finish in first. Now, one of the horses crossed the finish line. How many are out there that could possibly finish in second place? All right, Zara, Escadar, very good. Caroline, Emily, very good. 4. And then this continues, right? Now there's 3 horses left on the track. Then there's 2 horses left on the track. And then there's that 1 horse still out there that's going to finish last. And so if I want to see the number of different ways they could finish, I can use the fundamental principle of counting, find a number of possibilities for each space, and multiply those together. And I get 5, 4, 3, 2, 1. And that's 120. Well, that's terrific. But, if this problem had said, it's the Kentucky Derby and there's 20 horses in the race, and now I'm looking at 20 times 19 times 18, like there's got to be a shortcut way to write this. And sure enough, there is. When we look at what we've done here with 5 times 4 times 3 times 2 times 1, if we want to start at a specific number and reduce it by 1 and multiply all the way down to 1, we have a shorthand way to write that. And it's that. It's not 5. It's not an exclamation point that way. It is an exclamation point, but not that way. This symbol is called a factorial symbol. And the way we would say this would be that's 5 factorial. And what 5 factorial means is 5 times 4 times 3 times 2 times 1. On your calculator somewhere, you probably have a button that's either just an exclamation point or X with and an exclamation point next to it. That's a factorial. That's what this is for. And so if you were to type in 5 and then that button, whichever button it may be, X factorial button, your calculator should give you 120. And because what it's doing is it's multiplying 5, 4, 3, 2, 1. It's multiplying all of those together. Just to try another one and just to sort of make sure we're good here, 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. So we start at 7. Yes, we are. All right, you're exactly right. 7, 6, 5, 4, 3, 2, 1, all the way down. And then if you do 7 factorial, you should get 5,040. And it's perfectly fine to just multiply them all the way down, but you can use a factorial button if you want to. One little note that I want to make about this, and it may not feel like it makes a ton of sense right out of the gate, but and we're not going to go into the mathematical proof of it. I'm never going to ask you for the mathematical proof of it. If we encounter 0 factorial, the value of that is 1. If anybody wants the mathematical proof of that, You can ask me by email and I can send it to you. But really, if you encounter 0 factorial, it has a value of 1. Okay, we had 3 things on our list for today: counting, permutations, and combinations. Now let's talk about permutations. A permutation is an arrangement of objects in which order matters. You might be thinking, well, how am I supposed to know whether or not order matters? It's a perfectly good question. And as we work through problems, I'm hoping you kind of see, oh, yeah, okay, this is where order matters. If we're arranging things, like putting books on a shelf, for example, if I put the English book next to the history book, next to the math book, if I arrange these differently so that it's math, then history, then English, the bookshelf would look different. So order matters because changing the order made a difference. Perfectly reasonable to be thinking, well, then what would be an example where order doesn't matter? I promise I'll give you some of those later on. For right now, a permutation is an arrangement of objects in which order matters. And we have a formula for working with permutations, and it's this. Pretty important for us to figure out that that exclamation point means factorial, because we're going to use that symbol right here in this formula for permutation. What we have here is n is the total number of objects and r is the number in use. In use might sound a little strange. What does that mean? Well, let's talk about our books on the shelf example. Let's say we have a total number of 9 books, but we only have room for 5 of them on the shelf. So the total is 9. The number in use, the number we can actually put on the shelf, would be 5. And these numbers will be I think they'll be really obvious for you when we start looking at problems of how the n and the r get put in there. Let's put this formula to work. 5 horses are going to be in a race. In how many ways can you arrange 3 of them in a line for a photo? So we want to arrange 3 of them in a line for a photo. Now, first thing I want you to recognize here is this. We are going to put these horses in a line for a photo. Well, if I put the brown horse on the left and the black horse in the middle and the gray horse on the right, that's going to look different than if I put the gray horse first. So order matters. Which means we have a permutation. Because how they would be lined up would make the photo look different. That tells us order matters. That tells us we have a permutation. There's a kind of a key word in here that's really helpful for us, and that's arrange. If I'm arranging things, order matters. That points me towards permutation. And our formula looks like this. And in this particular case, let's see, n is the total number of objects. Well, there's 5 total horses. I'm only going to arrange 3 of them in my photo. So here I have n is going to equal 5, and r is going to equal 3, because I have 5 horses, but I'm only putting 3 of them in the photo. There are 5 total, but I only have 3 in use. So what we have here is 5p3. A formal way to say this right here, and you could do this or choose not to. You could say 5p3. There's nothing wrong with that. The formal way to say that would be that this is a permutation of 5 things taken 3 at a time. That would be the formal way to say 5p3. This is a permutation of 5 things taken 3 at a time because we have 5 total, but we're only using 3 of them for this particular picture. First thing I'm going to do is show you how this formula works. And then after that, I'm going to give you another option for solving this. So let's plug in. N is 5, so I'll have 5 factorial on top. And on the bottom, I have n minus r factorial. Now we just need to simplify this thing. Parentheses go first, so I'm going to subtract on the bottom, and I have 5 factorial over 2 factorial. All right, you've got some choices from here, and I'm going to give you all those choices. But the one that I really like when you're doing this by hand is to rewrite 5 factorial. Factorial should definitely be on a scientific calculator somewhere. It kind of depends on what calculator you have, but we can definitely help you find that, Escadar. And I'm going to go one step beyond that here in just a minute, I promise. I'm going to rewrite 5 factorial as 5 times 4 times 3 times 2 times 1. And on the bottom, I have this 2 factorial that I could write as 2 times 1, but hang on a minute. You know, when I rewrite this as 5, 4, 3, 2, 1, this right here, just this part, 2 times 1, I could rewrite that as 2 factorial. I don't want to go too fast here. I want to be patient and careful. What I've just done is I've rewritten 5 factorial this way. And what I wrote was 5 times 4 times 3 times 2 times 1. The reason I stopped at 2 factorial is because when I look at my denominator here, I have 2 factorial down there. And by stopping at 2 factorial, I can cancel those. Now all I'm left with is 5 times 4 times 3. And I can see that there are 60 ways that I could put these 3 in a line for a photo. Oh, yeah, you might have an exclamation point. You might have X with an exclamation point. I also want to tell you one more thing. Chances are your calculator has a button on it that is NPR. What that button will do is it will take you from here to here. So I love doing this by hand and canceling stuff out and multiplying what's left, but your calculator likely has an NPR button on it. It will do the calculation of this permutation for you. And most likely the way to enter this, again, kind of depends on your calculator, but is 5, then the NPR button, then 3, and then either enter or equals. And what this will do is give you the 60. When I said earlier today, I don't think you'll have trouble with the calculation. I mean that, whether you're doing it by hand or if you're using your NPR button to do the calculation for you. It's not cheating, it's perfectly fine. Your calculator has the button, you've learned how to use that button. Please don't feel like you have to do this by hand. I think doing it by hand is a pretty cool process. It goes pretty fast, but please feel free to use that permutation button if you want to. Are there questions about what we did here before I have you try one? Okay, here goes. Sophie has 8 unicorn figurines. She's going to arrange 5 of them in a line on her dresser. How many different ways can this be done? So, figure out how many ways Sophie can arrange those unicorns on her dresser. I am going to make a poll for this one and give you a chance to try it. One thing I will say, if you're having trouble finding your NPR button, if you have a TI-30XS, there is a PRB button up near the top left corner. That one is where your factorial, your NPR, and your NCR that we'll use in a little while, that's where all those are located, is behind the PRB button in the top left. Or you can do it by hand. That's good too. Let's go another 20 seconds on this, and then we'll do it together. Gotcha, Stephanie. We can talk about that after we finish this up. And of course, calculator batteries fail. Forget to bring a calculator to an exam. Great to know how to do it by hand, and these aren't that hard to do by hand. So I think they're kind of fun to do by hand, but maybe that's just me. All right, let's take a look and see where we are on this one. Okay, really strong agreement, not unanimous, but strong agreement, that's good. Make sure to let me know if you have any questions. All right, so let's go through this. Sophie has 8 unicorn figurines. She's going to arrange 5 of them in a line on her dresser. She's going to arrange these figurines in a line. So order matters. That's step 1. And honestly, what you're going to find in this section as we talk about it is the hardest part is deciding whether it's a permutation or a combination that we'll talk about in a little bit. So order matters. That means this is a permutation. So we have this formula that we're going to use. And in this particular case, Sophie has 8 unicorn figurines and she's going to put 5 of them in a line. So this is a permutation of 8 things, taken 5 at a time. Now we'll plug in and we'll have 8 factorial over 8 minus 5 factorial. And we'll simplify. That's 8 factorial over 3 factorial. And now I'm just going to rewrite that 8 factorial on top. And as I do that, I kind of know I've got this 3 factorial in the bottom. So when I get there, I'm going to stop. So it's going to be 8, 7, 6, 5, 4, 3, 2, 1. I wrote the 3, 2, 1. I just wrote it like this because in this particular problem, that was a convenient way for me to write it because I have this down here and I can cancel those with each other. On the bottom, I have that 3 factorial, and now those cancel, and I'm left with 8 times 7 times 6 times 5 times 4. 6,720 ways that Sophie can arrange 5 of her 8 unicorns on a dresser. Sounds like a big number. 6,700 ways? Yeah, sure enough, if you start listing them out, if all these unicorns had names A, B, C, D, E, F, G, H, and we went, okay, well, our first arrangement is A, B, C, D, E. Then our next one is A, B, C, E, D. And then our next one is A, B, D, C, E. And then, oh, okay, I haven't even brought F, G, and H into it yet, and I could see how this is going to be a whole lot. I'm good with the 6,720. It's kind of what I'm hoping happens in your head. You definitely don't want to list them out. If you're using your NPR button, then you're just typing 8 NPR 5, and then either enter or equals, and that should get you to 6,720. Stephanie mentioned that it's below the parentheses. Actually, Stephanie, and this is going to sound weird to you at first, it's actually above the 9 is where it is. And up in the very top left, you'll see a green button that says second on it. What that button does is it allows you to use what's up on the second story. And so if you look at the number 9, up above it, sort of on the second floor, is that NPR button. And so it's the second key that allows you to access those things that are up above the button itself. So what you would need to do there is 8, and then hit that second key, then the NPR button, and then the 5, and then equals. Eskedar, I think yours is a little different. If you have the TI-30XA that Stephanie mentioned, doesn't have a PRB button. Really? So let's walk through this real quick here. So you did, let's make sure we're entering the right thing. We did 8, second, and then the number 9, because that's how you get your NPR button, and then 5, and then equals. Those should be your keystrokes. So 8, second, hit the 9, hit the 5, and then equals. Perfect. Very good. Very good. That's excellent. Awesome. And that's okay too, Zara. Not a problem at all. You know, what you'll find if you do it by hand is it goes pretty quick. It doesn't take very long. But if you want to use the button on your calculator, there's absolutely nothing wrong with that. I want to make sure that you don't feel like you're cheating or anything, because you're not. You're not. You learned how to use that button, and that's fine. If anybody is confused about how to make your calculator work, it's okay for us to talk about that. That's not a problem. Oh, well, that's true too. No, absolutely. Desmos is a great tool. You bet. You bet. Okay. One more permutation question, just to make sure you've seen one of these. So if one pops up, you're not surprised by it, is 6P2. The real world questions, you know, are terrific. Sophie's going to arrange her unicorns. But sometimes you might be given one that's just a straight, here's a permutation, 6P2. And okay, well, that's a permutation. So I'm going to use the permutation formula, which is NPR is equal to n factorial over n minus r factorial. And so we'll plug in. And here we have 6P2, permutation of 6 things taken 2 at a time. And we'll have 6 factorial on top, 6 minus 2 factorial on the bottom. And so that'll be 6 factorial over 4 factorial. And we'll rewrite it. I know I've got that 4 factorial on the bottom. So when I rewrite this, I'm keeping that in the back of my mind. And I'll have 6 times 5 times 4, 3, 2, 1 on the bottom. I'll just leave that there. Those cancel. 6 times 5 is 30. Like I said, doing these by hand with the canceling is, you know, it's not really a burden. So if you want to use a calculator button, great, but you don't have to. Does anybody have questions about what we've done here with permutations before we move on to combinations? All right. We mentioned before that permutations is when order matters. A combination is a collection of objects in which order doesn't matter. Right now, it may be hard to think of, well, when would order not matter? Here's an example. There are 15 students in a classroom, and 5 of them are going to be chosen to stay inside during recess to help clean the room. Now they're just going to be chosen. And the first person chosen and the last person chosen, there's no difference. The order that they're chosen in, being the first person picked, being the last person picked, it doesn't matter. It's the same. You're either cleaning the room or you're not. The order doesn't matter. That's an example of order doesn't matter. The formula for combinations is very similar to permutations, but it does have one little difference in it. Well, I guess two. It has a C in it, and then n factorial on top, and on the bottom we have r factorial multiplied by n minus r factorial. So the only differences here is the C for combination, but then we have this r factorial out in front. The reason for that, the reason it goes there is if we were talking about a permutation, these two things would be different from each other because order would matter. Now with a combination, order doesn't matter. AB is exactly the same as BA. So we don't want that to count as two things. We only want it to count as one. And so that's why we have to divide by something else to lower the number of possibilities, because we don't want the duplicates to count twice. So that's our new formula here for combinations. And the key is we have combinations when order doesn't matter. Also, somewhere close to your NPR button is probably an NCR button. Perfectly fine if you want to use that. I'll do them by hand. Nothing wrong with using that button. Let's take a look at one. A student can pick 3 of 5 essay questions to answer. How many different ways can the student pick the questions? Notice, this didn't say what order they're going to answer them in. It just said how many ways can they pick them. They're either going to answer the question or they're not. It doesn't matter which one they do first, second, or third. So here, order doesn't matter. They're not arranging the questions. They're not lining the questions up. They're just picking them. And so order doesn't matter. And that means we have a combination, which means the formula we're going to use is this one. N is the total number of objects. R is how many we're using. And here there are 5 total questions, and they're going to pick 3 of them. So we have 5C3. The formal way to say this, which I won't ask you for, but in case you want to know it, is a combination of 5 things taken 3 at a time. That would be the formal way to say this. And we actually have a shorthand way of saying this one that we didn't have for permutations. A shorthand way, sort of a less formal way to say this is 5 choose 3. So this is 5 choose 3. That we don't really have a shortcut way for permutations, but we kind of do for combinations. So we could say 5 choose 3 for this one. Let's plug it into our formula and see how this one plays out. We'll have 5 factorial over r factorial n minus r factorial. Okay, so this is a little more complicated than what we did with permutations, but not a whole lot. We've got 5 factorial over 3 factorial, 2 factorial. Doing this by hand, there is one danger I want to make sure to point out to you, and it's this. 3 factorial times 2 factorial is absolutely not 6 factorial. So we do not want to do that. Keep in mind what 3 factorial means 3 times 2 times 1. 2 factorial means 2 times 1. There's no 6 anywhere. There's no 5 anywhere. There's no. We're not going to do that. We're just going to leave it as 3 factorial times 2 factorial down there on the bottom. When I go to simplify this, I'm going to rewrite my 5 factorial, and I'm going to look at these two numbers and say, well, which one's bigger? I want to stop as early as possible. So the 3 factorial is the one that I'm going to cancel with. So when I rewrite 5 factorial in the numerator, I'm going to go 5 times 4 times 3 factorial. That 3 factorial is going to stay in the bottom because I'm going to cancel it. And the other one, the 2 factorial, I'm going to go ahead and write that out as 2 times 1. And now I can cancel the 3 factorials. And there's a couple of ways you can go from here. What most students prefer is multiply what's on top and get 5 times 4. Multiply what's on the bottom, 2 times 1, and end up with 10. How many different ways could a student pick the questions to answer? 10 different ways. I said there's a couple of different ways you could go. I'm going to back up just a minute. You might like this. You might think it's terrible, but what you also could do once you're here is you could say, you know what? Dividing by 1 is not going to do anything. And 2 will go into 4 twice. And so now all I'm left with is 5 times 2, and that gives me my 10. If you really like canceling all kinds of stuff and canceling as much as possible, then this approach will be something you like very much. If you'd rather say, you know what, I'm good here. I'm going to multiply 5 times 4 on top, 2 times 1 on the bottom, and then divide to get to that 10. Nothing wrong with that either. Also, if you want to use the NCR button on your calculator, that's okay too. And this would be 5, choose 3. Are there any questions about what we did there to solve that combination problem before we look at one more? And I promise I will give you a chance to try combination problems, but not quite yet. Well, they were wrong, Genesis. You're allowed to have a calculator. You definitely are allowed to have a calculator. I apologize that they told you that. We might need to talk about where you took that one so that I make sure that they understand your instructions correctly. Really? Huh. Well, they have instructions from me that have the password on it that say you're allowed to use a calculator. So yeah, we'll make sure that that's okay, good. Yeah, Canvas has one built in. So and it's perfectly okay for you to use it, but they should have let you have one. I apologize for that. Yeah, they definitely should have let you have one. And that's something we can talk about later on, and I'll make sure that that doesn't happen on exam 2 and exam 3. Another combination question. A student can pick 3 of 5 essay questions to answer, but question number 1 must be answered. How many different ways can the student pick the questions? This is a little bit like when we were doing those problems at the beginning of class today without replacement or without repetition. You can't, once you've used it, you can't use it again. This is similar to that in that there are 5 essay questions and the student gets to pick 3, but they have to answer number 1. So what that really means is they don't really have 5 to pick from, and they don't really get to choose 3 of them because they have to do number 1. So what that means, of the remaining 4 questions, they get to pick 2. So the fact that question number 1 must be answered, that limits this a little bit. It changes the structure a little bit. Instead of there are 5 and you get to pick 3 of them, now really there are 4 and you get to pick 2 of them. So this one is just in the language of the question a little bit, that it brings it down to 4 choose 2. We'll go ahead and work through this one. Let's see, we'll have 4 factorial over 2 factorial, 4 minus 2 factorial. And so that's 4 factorial over 2 factorial, 2 factorial. Now we're going to simplify this, and we have 2 of these down here. We're only going to be able to cancel one of them. So when we do that, we're going to go 4 times 3 times 2 factorial. That's going to cancel one of them. The other one I'm going to go ahead and write as 2 times 1. And what happens from here is my 2 factorials cancel. And I have 4 times 3 is 12 over 2. So there are now 6 different ways the student could choose to answer the questions. Essentially, if you see something like this where it says, you know what, there's 5 of them and you're going to answer 3, but you have to answer number 1. All that does is sort of limit the total number of objects and the total number that are going to be in use. Are there questions on this before I have you try a combination problem? Okay, here goes. Very straightforward. 6C2. So this is a combination of 6 things taken 2 at a time. We didn't do a poll for the one like this with permutations. So we'll do a poll for this one with a combination. You can use the formula to do this one by hand, or if you're comfortable with the NCR button, that's totally fine. You might see word problems that are permutations, combinations, counting principle. You might see problems like this where it's just straightforward. Use the formula for combinations to find out how many ways you could choose 2 things from a group of 6. We'll go another 20 seconds on this and then talk about it. See where we are? Unanimous. Very good. That's excellent. All right. If you have questions, let me know. I'm going to go ahead and work through this one for us then. So let's see here. The formula for a combination, NCR, is n factorial over r factorial, n minus r factorial. And here we have 6 choose 2. So that'll be 6 factorial over 2 factorial, 6 minus 2 factorial, or 6 factorial over 2 factorial, 4 factorial. I could cancel either one on the bottom when I rewrite this, but that 4 is the bigger number, so that's what I'm going to get rid of, and I'll have 6, 5, 4, 3, 2, 1. That's going to cancel with this. The other one, I'm just going to write it out as 2 times 1. These will cancel, and it looks like I've got 30 over 2, which is 15. If you're comfortable using the NCR button, that's totally fine. Any questions on this before I have you try one more combination problem? All right, here goes. Malcolm is going on a trip and will choose 4 of his 11 t-shirts to bring. How many different ways can he choose his shirts? First thing I want you to notice here is he is just going to choose the shirts that he brings. This isn't about arranging them in a closet on hangers or anything like that. He's just choosing them. They're either going on the trip with him or he's not. What that means is that order doesn't matter. And that means we have a combination. Okay, I'll set up a poll for this and have you try it. This one involves some bigger numbers. If you wind up with something that's not one of the choices, go ahead and pick one that's closest to your answer, and then we'll sort that out when we get a chance to talk it over. Go another 30 seconds, and then we'll do this one together. See where we are on this one? Okay, agreement, not as strong as we've had most of today. So let's be a little bit careful as we go through this one together then. A key here, probably the most challenging thing for you to decide when you work these out is this a counting principle problem? Is it a permutation? Is it a combination? The fact that order doesn't matter means this is a combination. And so the formula that we're going to use needs to be the formula for combinations. Or if you're using a button, make sure you use the NCR button because this is a combination, not a permutation. And here there are 11 shirts and he's choosing 4 of them. So this is 11 choose 4, which will be 11 factorial over 4 factorial, 11 minus 4 factorial. Or 11 factorial over 4 factorial, 7 factorial. I want one of those to cancel on the bottom, so I'm going to rewrite this 11 factorial as 11, 10, 9, 8, 7 factorial, because that'll get rid of this 7 factorial I have down here. The 4 factorial, I'll just write that out as 4, 3, 2, 1. Those will cancel. And now you can multiply across the top. 11 times 10 times 9 times 8 is 7,920. On the bottom, we have 4 times 3 times 2 times 1. That's 24. And then we'll divide those. 7,920 divided by 24 and end up with 330 ways that Malcolm could choose 4 shirts to bring. If you really like canceling stuff, you may have said, well, dividing by 1 doesn't do anything. And let's see here, 4 times 2, get rid of that 8, and 3 will go into 9 3 times. And so it's 3 times 11, that's 33, times 10 is 330. Didn't need a calculator at all. But that's just me having fun canceling stuff. If that's not the way you went about this, that's totally fine. If you use the NC bar button, that's totally fine also. One last thing I want to say is I mentioned that probably the toughest part of today will be deciding, is this problem a permutation or a combination? And some things that can kind of help you with that are some key words. These words might not always be in every problem. They will often. And I also have something else to say about that in just a second. But if words like arrange or order are in there, this is going to indicate to us that order matters. If I'm going to arrange things, then order matters. If instead I'm just going to pick them or choose them or select them, I'm not putting them in any order, I'm just picking them, then order doesn't matter. And that tells me I have a combination. If you happen to see one of these words in the problem, it's a really good sort of clue. Also, if you don't see one of those words, what you could try to do is try to replace the words you've been given with one of these, and then see if it makes sense. If it makes sense to, oh yeah, this is an arrangement I'm making. These things are going in a certain order, so order matters. Or I'm just choosing here. Order doesn't matter, and that's how to decide combination. The only other thing I want to mention is we spend a lot of time on permutations, combinations. They have formulas. We have calculator buttons. Please don't forget about the fundamental principle of counting at the very beginning of class. If we're talking about a garage door code that has 4 different digits, don't try to force permutation or combination on it. Some of the problems will just be, how many choices are there for each space? Multiply those together. Don't forget about the fact that those problems are in here too. It's really easy to get kind of so dialed in on permutation and combination that we forget about the fact that, oh, this is one where I